Policy procedures require the ability to exchange information between operations. The output from one operation or microservice may need to be input to the next operation, microservice. Web services exchange information through messages sent over the network. When the services are performed on the same platform, a more efficient way to exchange information is needed. The mechanisms that are used to manage information exchange include encapsulating the information in a file. The file can be read by the next operation. This incurs at least a disk latency. Encapsulating the information in a message moved using network protocols. The information must be packaged into a format understandable by the service and will incur a network latency. Store the information as persistent state information in a database. The information is turned into metadata attributes. A database access latency is incurred on access through a query. Encapsulate the information in structures in memory. The information can be accessed directly by the next operation from the in-memory structure. Within a data grid, all four mechanisms can be used to exchange information. The primary information exchange mechanism is through structures in memory. When microservices are used within a rule, they put results into a data structure in memory, which is read by the next microservice. Information that must persist across access sessions is stored in the ICAT database and retrieved through database queries. The IRODS data grid uses an in-memory structure to store information and data called REI, Rule Execution Infrastructure Memory Structure. Memory structures can be defined to support passing of values between microservices. For instance, session variables correspond to elements within the REI structure. Microservices can store workflow variables in memory, such as buffers, an example is standard out, integer variables, string variables, Boolean variables, and key value pairs, such as results from a query. The IRODS network protocol packages information for exchange between servers. See wiki.irods.org, index.php, IRODS protocol overview. Packing instructions are used to serialize arbitrary C structs for transmission of the in-memory structures to a remote IROD server for execution of distributed rules. At the remote server, the messages are unpacked back into in-memory structures for use by microservices at the remote site. Each packing instruction is given a name. It is possible to pack or serialize data types, arrays, strings, pointers, an array of pointers, and even structs within a struct. This makes it possible to execute rules that use microservices on multiple servers. The required information is packed and sent over the network. The exchange of information between microservices running on different storage locations requires the use of the IRODS protocol. The IRODS middleware can send messages between servers to do the following operations. Establish a socket connection, RODS connect. Disconnect the socket, RODS disconnect. Send packed information, RODS API rec. Return the results, RODS API reply. Authenticate to a federated data grid, RODS reauth. Verify version compatibility, RODS version. A packing instruction is defined for each data structure that defines how to linearize the structure for transmission over the network. A corresponding unpack instruction defines how to recreate the appropriate in-memory structure. An implication is that rules can be created that are executed on multiple servers, and the data grid middleware will keep track of the information exchange for you. Take 7 minutes and complete exercise 116. Compare the advantages of storing information in a file or as metadata, persistent state information in the metadata catalog, or in in-memory structures. Please load a paragraph describing your decision into the lifetime library in the sub-collection class INLS 624 by the end of today's class. The DataBook project is an initiative within the DataNet Federation Consortium to link researcher information, datasets, and workflows. DataBook provides the identification of relationships between researchers, datasets, and operations performed upon the data. Causal relationships are tracked by identifying events that identify access by users or use of an application or operations performed upon the data. The information about the use of the data can be used to promote sharing of data, workflows, and policies. A researcher can identify work being done by other persons or data sets that are used for a particular analysis or operations that are performed upon a particular data set. Collaborations can then be formed based upon similar analyses of similar data sets. A second objective is recording information needed for reproducible research. If events can be identified that track all of the processing steps on input datasets, a complete description of the analysis becomes possible. The DataBook project is an example of an asynchronous federation of multiple systems: Vivo, Elasticsearch, Message Bus Technology, and the iRODS data grid. The Vivo technology supports information about researchers and related entities. The technology is open source and is available here, www.vivoweb.org. Vivo is a semantic web application that is being developed by Cornell, Duke, and the University of Pennsylvania. The Vivo system is designed to capture relationships between researchers and publications. The extensions being implemented by DFC are the creation of relationships between researchers and datasets, between datasets and operations, and between operations and researchers. The DataNet project's Sustainable Environment Actionable Data uses the Vivo interface to manage information about researchers and publications. An interoperability demonstration was developed that linked the Vivo instance used by SEED with the operations performed upon datasets within the DFC Federation Hub. An interface was developed based on message bus technology to track events related to data ingestion and data manipulation. User statistics could then be tracked about access by users, the usage of data objects, and the operations performed upon the data. A Sparkle query could be made to Vivo to retrieve the information. An application of these capabilities is the identification of communities based upon common usage patterns. The entities that are tracked by DataBook include data objects. This is any entity registered as a digital object within a collection, including files, workflows, links to external resources, queries, and rules. Collections. Every data object is associated with a collection. Each collection is associated with a parent collection, forming a collection hierarchy. Metadata. Descriptive metadata can be added to any object in the iRODS data grid, including users, files, collections, storage resources, and rules. Comments. Comments can be added as metadata about users, resources, and files. Like, dislike. Annotations can be added to objects indicating interest. Access history. Event trails can be generated identifying all access events. Events. Access to policy enforcement points can be captured as events that identify the operation and object. Sessions. Each user access corresponds to a session. Within a session, multiple rules can be invoked that manipulate data objects. Workflows. Provenance of workflows such as input parameters and input files can be automatically recorded and associated with the output files. Each workflow execution instance can be versioned and recorded. Versions. Versions of files, workflows, metadata, and operations can be defined. The interaction mechanisms between the DFC Federation Hub and DataBook are shown here. The DFC Federation Hub is indicated on the right, with federated data grids for each participating discipline. When a user submits a file for storage in the DFC, an event is generated that is sent to a DataBook user interface that in turn accesses the Vivo user interface. The information is deposited into the Vivo middleware through a DataBook interface. The DataBook Ontology is applied to create relationships for deposition of the information into a triple store. Events created by DataBook rules can also be deposited into DataBook through the DataBook middleware. Queries are made on the triple store to retrieve statistics that are presented through the DataBook user interface. For this demo, an Elasticsearch triple store was used.